When will we finally discover another Earth-sized world orbiting around a sun-like star within the habitable zone of its star, like place that there could be life? And it's going to be a while. That's because the light from the star is so bright, you have to be able to block it to reveal the planet beside it. That's in the visible wavelength. It gets a lot easier in the infrared wavelength. And so a new NASA grant has been awarded to Dr. Heidi Newberg, who is a researcher at Rensselaer Polytechnic Institute. And her proposal is called the Diffractive Interfero Coronagraph Exoplanet Resolver, or DICER. And it involves this really interesting quirk with physics where you can use a grating to diffract light into a telescope. And the telescope isn't pointed directly through the grating, but actually at a angle, and so you get a very specific wavelength of light coming through the grating and into the telescope, and hopefully this will allow a telescope that's relatively small to be able to reveal a planet orbiting around a sun-like star. It's a fascinating concept, has some technical challenges to overcome, and yet, if it does work, could be an important new tool for future space observatories. All right, here's the interview. How tricky is it to observe the Milky Way? I mean, like, we're stuck inside of it. It's like trying to observe your house from the inside.
Yes, my students have said it's like trying to make a map of New York City by standing on a street corner. And and it is. It's one of the last, so before surveys like the Sloan Digital Sky Survey and TUMAS and the surveys that have done the whole sky, and now and most recently the Gaia satellite that surveyed the whole sky, we weren't really able to study the Milky Way very well. And when I started working on it in the 1990s is when I started working on it myself. We really didn't know very much about the Milky Way galaxy compared to what we knew about other galaxies. And that's just because you can look at other galaxies in one telescope shot. You just shoot right at it and you get the whole thing, you get the whole picture of it. But for the Milky Way, even finding out what kind of a spiral galaxy, how big is the bar, how many spirals do we have, anything about the Milky Way has been hard to do because you need to get the whole sky. And we've only recently been able to do that with these big surveys. And now we can build up a picture of the Milky Way star by star. Right. And put it together and then be able to see what it looks like. So we have a much better idea.
Do you think we're normal?
The galaxy?
Yeah.
Is the galaxy normal?
Yeah.
It's a pretty normal galaxy, I would say. In fact, we try to use it as an example of how galaxies form. That's one of the things is that in the Milky Way, we can observe, even though it's hard to see because you have to look every direction. There are things you can find out about the Milky Way you can't find out about other galaxies because we see our galaxy in 3 dimensions and we see other galaxies in 2 dimensions. And that 3rd dimension gives us a lot more information about how it dynamically works. And so I like to try to use the Milky Way and its dynamics and try to understand its history and how it formed so that I can learn about other galaxies and how they formed. And so I think it's a good example of a spiral galaxy and a good example that we can use to try to understand. We call it near field cosmology, understanding how the universe formed, the cosmological context of our universe by looking at things that are very close to us, which is not what they used to do. They used to only look at very distant things to understand cosmology.
Now, your primary research is in the Milky Way and the structure of and I'm sure Gaia has been just a revolution on that.
Huge.
Yeah.
It's huge.
Yeah. I think that's my favorite observatory, my favorite mission right now. And I'm just like, it feels like every question you can ask is answered by the Gaia survey.
Yeah, unfortunately, we have to figure out the answers ourselves, and that takes a while.
Yeah, it's in there.
I think it's in there. It's in there, but it might take a decade to get it out. I have some experience with that. I was probably the first postdoc on the Sloan Digital Sky Survey years ago, and when the data from that came out and was public, we learned a lot about the Milky Way and lots of other subjects. But the paper that we published in 2015, where we found the ripples in the Milky Way, huge result that came out of it. That result was made with data that had been publicly available to everyone in the world for a decade. And so these huge results they're in these big databases, and it does take a while to figure out exactly what's in there and what the meaning is. And that's my expectation for Gaia as well, that we will eventually learn a lot that we don't know already.
I mean, it's interesting. It feels like there's a bit of a shift. Like in the olden days, people would book time on a telescope to answer a very specific question. They would take their data, they would crunch it, they would produce a result, and then they would publish. But now, with the rise of these giant surveys, there's so much information that's just been collected en masse, trawled from space itself, and now you just have to be a good detective to look through this data to start to piece together the clues. Does it feel like things are shifting to that model of astronomy?
Oh, definitely. And in fact, so the prototype experiment that caused that shift was the Sloan Digital Sky Survey. Mm-hmm. And so, part of what we were doing on that survey, it was not just designing a survey, but creating a culture and a process in astronomy that allowed astronomers to work as big collaborations. I at the time I was at Fermilab, and Fermilab is a particle physics laboratory where they have been doing huge particle physics collaborations for a very long time. But until the Sloan Digital Sky Survey, astronomers are usually, me and my postdoc or me and my graduate student, and we'd write a paper together. And astronomers, had a completely different culture. There were people who liked to go to mountaintops at night by themselves. And so you can imagine trying to get people who are in that kind of mindset to work together on a big project. I mean, people didn't even know, whose names are we going to put on the paper?
Right, right.
Am I really going to let my graduate student go spend 3 years writing software for a big project and not doing any science? And how will their career work? I mean, these were all real issues that we were trying to solve. And I think we did a great job as a collaboration at figuring out how to work together and how that was going to work in this. And we did some things differently from the high energy physicists. And I think that all of the big projects in astronomy since then have kind of used it as a model for how it is that we do science as a group.
Right. Yeah. Yeah. All right. Well, let's talk about the telescope idea. So,
Okay.
The problem is that you're such an expert in these other fields that I'm really fascinated in. But I think
I'm all over the place.
Yeah, me too. So, but let's talk about it. So, you recently awarded a NIAC grant for a pretty unique idea for a telescope. So, can you explain it?
The idea is so I'll tell you what the problem is. The problem in exoplanets and finding Earth-like exoplanets is that you would like to look for Earths in the infrared. Why do you want to look for Earths in the infrared? Well, because the Earth is bright in the infrared. That's what, our black body radiation, our temperature would cause us to emit light in the infrared, and the sun is bright in the visible. And so if you try to look in visible lights, then you have to then the sun is very bright and it makes it hard to see the Earth because these exoplanets are very close to the star. But you also, when you look in the infrared, you want to also be able to you want to be able to see a picture where you can separate the star from the planet, because even in the infrared, the sun is 1 million times brighter than the Earth. So you need to be able to separate them in your picture enough that you can block out the star that the planet's going around and see the planet that's going around it. And you can do with your basic physics, probably high school physics, definitely the first year in college physics, you can write on the back of a napkin the equation for how big a telescope you would need to resolve a star like the sun from a planet like the Earth out to distances where we could expect to find such planets. And the answer is you need a 21-meter telescope.
Right. And that's just the telescope not
That's
necessarily
the diameter of the telescope.
Right, and that's not necessarily the coronagraph that's blocking the light from the star.
Right, that's a whole other problem.
Right.
But so if you look at James Webb is a fabulous achievement. It took a very long time. It had a lot of moving parts. They had to fold it up inside the launch vehicle and then unfold it and calibrate it and do all these things. That's a 6.5 meter telescope. And the space community has pretty much come back and said, no, we can't really build it bigger than that yet.
Right.
So there's a disconnect between the 6.5 meters, which we can get, and the 21 meters we want.
Yeah. And I know with
the
recent decadal survey, they walked back from the LUVOIR concept, which would have brought you into that range in the 12 to 15, maybe 20 meters. Which
that's
would be
why they wanted it.
Yeah, which would be wonderful. But now it looks like it's going to, whatever it is, it's going to be something in the same class as Webb, but with a different spectrum.
Right. So there's that science that people wanted. That LUVOIR was walked back, HABEX was walked back, and so there's this like need for something that can do that job. But what people came back and said, we don't have the technology. Our technology isn't ready to do that. Maybe in the future, but not yet. And so this is an idea that kind of comes from a different direction with a new kind of technology that I'm hoping will be able to solve that problem in a shorter time scale, maybe less expensively. So the idea is, instead of having one big monolithic 20-meter telescope, we're going to put two diffraction gratings out there. And a diffraction grating, like a lens, it bends light, but it does it in a different way. And they're flat. Lenses have to be curved. Diffraction gratings are just a flat piece of, glass or anything else. Could be a reflective or a transmission grating.
I think like a Fresnel lens. Is that sort of the same technology?
A Fresnel lens is the same kind of technology, but the Fresnel lens is what we call a focusing optic.
Okay.
And so it acts more like a lens. What I'm talking about is one that will not focus. And so that's why we have to have a focusing element. So we put something that's like an infrared telescope that catches the light. So that the light comes in, it hits the diffraction grating, then it's diffracted off to the side. And then we put this focusing optic that catches the light that's coming off to the side, that's diffracted through here, and then focuses that to the focal plane.
Right.
And so we're collecting light over, so maybe 2 10-meter gratings. We think maybe we can actually get it down to maybe 2 5-meter gratings, where this part of our proposal is to try to figure out exactly how big these gratings have to be. But you could imagine, folding them up and in a launch vehicle and then unfolding them, in an easier way than maybe the James Webb. It's just flat things that have to go out. And then we catch the light with 2 of these smaller telescopes. And one of the things in our proposal is to figure out how small can we make them. Our prototype has 2 3.5-meter telescopes, and that's smaller than 6.5, but it's still pretty big things to put in a launch vehicle.
Now, sorry, are these multiple telescopes, are they bolted together or are they free floating?
Yes. No.
Right.
It's bolted together. So
I'm thinking like the large binocular telescope, as opposed to where you've got sort of 2 telescopes that are separated, but they are separated by a known amount, as opposed to like an interferometer where you're floating and changing the distance.
Yeah. So we use an interferometric technique to remove the light from the host star. So we have kind of an interferometer, but it's bolted on. It's not a free floating kind of interferometer. And it isn't what's giving us the resolution. Our interferometer doesn't give us the resolution. It gives us the reduction in the light from the star. The resolution is coming from these gratings that are the thing that your physics it says there's a limit to how much you can resolve something, and they're giving you that limit by floating out there.
Now, when you say
okay.
floating again, are they free floating separate from the?
Nope,
No. Okay.
bolted to it.
So the whole thing. So I'm imagining a space version of the Large Binocular Telescope where you've got two telescopes side by side, and then ahead of them there's a grating, like sunglasses for the telescope that is performing that process as the light's coming through.
Right. So the one thing that we make that's a little bit different than what you're imagining is you would like to take, instead of the two telescopes pointing up with gratings over the front of them, the telescopes are going to be pointing at the gratings this direction. So here's the light coming down, comes to the grating, they go this direction. And that's how, so if you had a 5-meter grating or a 10-meter grating and you wanted to put a telescope behind it and catch the light from it, it would also have to be 5 or 10 meters. Right? But if you put the telescope on the side, then it can view this whole grating and be a lot smaller.
I see. So the grating, as you said, can diffract the light.
Right.
And it's being diffracted into the aperture of the telescope.
Right.
And then you're taking advantage of some fancy physics to do this. So let's talk about the fancy physics, because this sort of sounds like a little interesting to me. Nothing that I've ever heard of before. So I guess
so it was a lot for me to take in when I started it too.
Right. So I guess what are you relying on? Right. You've got this grating. You say it can diffract. You've got your smaller telescopes that are pointed at a pretty severe angle, just getting some kind of incidence refraction coming from the grating. So what are the underlying physics, optics that you're taking advantage of?
So the only optics we're taking care of is the diffraction from the gratings and the focusing of the telescope and the interference from the two telescopes that we put together to get rid of the light. It's all physics that people have used before, but have never put them together in quite this combination. There have for many, there's historical telescopes that used a GRISM survey where they put a grating in front of a telescope. So they did, the thing where you just put a grating right over the top of it. And if you do that, then it can spread the light from the star out into a spectrum. And in the focal plane of the telescope, you get a whole bunch of spectra of each object, all on top of each other. But if you don't spread the light out very much with this grating, then you have little short spectra of each object, and you can get kind of a sense of what the spectrum of each thing looks like. If you, instead of pointing the telescope up at it, if you move the telescope off to the side, then what the diffraction, the grating equation tells you is that the portion of the spectrum that you will detect becomes much smaller. So we see a very, very small piece of the spectrum of the light from an object. And so we can get a very big area collection. So we collect a lot of photons on this area, but then in the telescope, we only collect a very small wavelength range of the light from that. So we've done the math for this, and you get about the same amount of light from an object in the sky if you take your small telescope and you point it directly at the object, as you do if you point it at this grating. Because the bigger the grating is, the bigger the angle it has to diffract at, and the smaller the piece of the wavelength range that you get.
And so, sorry, I'm still trying to kind of wrap my head around this. So like I know, if you're going to try to do this in the visible spectrum, we talked about that 21-meter telescope. And
we want to do in the infrared.
Yeah, I know, I understand that. But if you were doing it in visible, and you're, having to decrease the light from the star by like a billion to just get that planet to be revealed. So by going in the infrared, you're changing that now. You merely need to dim the star by a factor of 1 million, which is vastly easier. And so I guess, you're decreasing the wavelength down to a very specific wavelength. So is it expected that there is a wavelength of infrared that's coming from the planet that is very specific, that is different from just the sort of the fire hose of infrared photons that are coming from the star itself? Is that the key?
No, that's not the key.
Okay.
So that may end up, we're kind of exploring that as a possibility, although I don't know what the answer is going to be as to what we can get. But our current model doesn't rely on having specific, very narrow frequencies that we try to find. In fact, finding a narrow frequency is kind of a downside. We don't want to get a very narrow frequency. We'd rather get a much larger range.
Got it.
But if we did that, we would need to get a much bigger telescope, and then we're back to problem one.
Right. I mean, I know that, for example, like telescopes like the Sphere instrument on the Very Large Telescope is looking at the polarization data of planets, and that gives you sort of a different way to detect them. But I guess that doesn't really help you in the infrared.
Well, that's not really an important part of our at least our current telescope design. What's important, what we're getting by putting the gratings out there, is the diffraction limit. I mean, so by having something that's a very long grating, you get the diffraction limit, which gives us a resolution. So we get to separate the planet from the star. That's the important thing that we're doing with the gratings.
Right.
Is getting that resolution, and we need that, because we don't have it, then again, it's the firefly in a headlight, and you can't see it.
Right. I mean, the difference. Sorry, like the difference between say the Event Horizon Telescope that gives you that enormous baseline and gives you that resolution versus something, say, the Square Kilometer Array, where you've got an enormous amount of total aperture that lets you see fainter objects. And it's that dichotomy. Like, if you're going to have a large aperture, you be able to see faint objects. And if you have a nice separation, then you get the resolution without necessarily seeing the fainter objects. But are you still requiring a coronagraph?
Yes.
Okay.
Yes, you still need a coronagraph because 1 million is a big number.
Right. But it's only 1 million, not a billion.
Yeah, right. I think it's like 10 billion. I don't know, a billion.
10 billion? Maybe. Okay. All right. Right.
Anyway, it's a lot better to look in the infrared. Anyway, so we still need the coronagraph, and what we're doing is combining the light from one side, one grating, with the light from the other grating, and we make sure that when they combine, they're out of phase, so that the object that we're exactly pointing at gets canceled out, and objects that are just off to the side actually end up getting imaged double. We see two images of something that's not directly in front of the telescope, but that's okay. 2 images is fine. So it's better than none. I guess,
what kinds of targets then can you find and observe with this version?
Our baseline science plan, that of course we're still working on this, is to look at the 60 or so stars that are G or K stars that are within 10 parsecs of the Earth. Now, so what does that mean? So the sun, our sun, is a G star, and G and K are measures of their temperature. And the G and K stars are stars that live a long time, so that life would have, billions of years to develop. And they're pretty calm. They're not shooting off jets of things and making the environment really difficult. And you can be far enough away, like an M, if you have an M, a very faint M star, and a lot of people have been looking for planets around M stars because it's easier to see a planet next to a fainter star. But the thing is that to get a planet that could have liquid water, you have to be very close to it, and the star has all these magnetic fields, and it's shooting off storms and things, and it would not be a lot of fun to live in an environment like that. So we're going for stars that are, in some sense, like the sun, in that they're a nice place for us to live. And so if we point it at those, there's about 60 within 10 parsecs, and what 10 parsecs is like 33 light years. Mm-hmm. 33 light years. The reason that we were kind of aiming for that volume is that no one really knows how many Earth-like planets there are in the universe. And if you go out to that distance, then the expectation is that we would find at least a few. Now, we don't know. Maybe we won't find any. Maybe we'll find 100. Nobody really knows how many Earth-like planets there are. But in order to have what we think is a good chance of finding a few of these planets we're trying to find, you have to go out to about that distance. And we would like to find all the planets that are close to us, because, if you found one, what's the first thing you'd want to do? Send a probe. You want to send a probe. And if the thing is, 100 light years away, then physics won't let you get anything back in less than 200 years. You can't even send a message and have them get it and respond. It would take 200 years. And that's really too long for our human life scale.
That's a different NIAC grant. Somebody else is working on that problem.
Yeah. But if it's like 10 light years away, you could imagine, communicating with it, at some level.
And I mean, I guess getting a survey of 10 parsecs around us and counting the number of Earth-sized worlds in the habitable zone of a G-type star gives you a representative sample for the rest of the entire universe.
Oh, yeah. Yep, you would think.
Yeah.
And think. We don't know.
Right. But the point here is that once operational, this telescope should be capable of directly imaging every single Earth-sized world orbiting one of these sun-ish like stars in our local vicinity.
Yes, that is the goal.
Wow.
And that is the goal. And the second thing that we're trying to do is to also be able to tell if there is oxygen in the atmosphere. That part is we're developing that a lot, and we're trying to figure out if we can do more than that, or what it would take to be able to make that measurement. But we would also like to say, and is there oxygen, basically. And that's one of the main markers for life, because if you look at our example of the Earth, it's our one example of an Earth-like planet that we use to try to extrapolate to what happens other places. But when life formed on the Earth, when you have photosynthesis, you make oxygen, and before that, you don't have oxygen. And so that's like something you want to know right up front. Is this going to be an Earth-like planet that has no plants, no life, no photosynthesis going on? Is this something where life has already started? And that's going to be a pretty important thing to learn as well.
And so once again, like, you are not only detecting the existence of the planet, but you're actually measuring the spectra of its atmosphere directly.
We're not really measuring. Yeah, this design, at least as it currently stands, because we're measuring. I mean, there's pluses and there's minuses, right? We're only able to measure a very, very small piece of the spectrum at a given time. And I'm working on trying to determine if there's a way to use that very, very small piece of a spectrum to directly get a line that would tell us whether there's oxygen or not. Currently, I'm not aware that we can do that because the absorption line in the spectrum that we have to look at is wider than our spectrum.
Right.
So the absorption. So what we're looking at doing currently is to take an observation in the middle of the line, an observation to the left of the line, and an observation, on either side. So we take one measurement here, and one in the middle.
That's really interesting.
Did it go down or not there? That
the spectrum of the absorption line doesn't fit. That it is outside of the range of what this telescope would be doing. So you're taking advantage of the fact that infrared is easy, but on the downside, interesting atmospheric observations fall in other wavelengths that you're just not detecting. But I like the hack.
Well, they're interesting. Yeah, it's in a broader. There are interesting observations in the infrared, but you need a broader wavelength range to see the whole thing. And this technology isn't. Right, it isn't possible to deliver that. at least the way we currently have it. I mean, there's a lot of ideas on the table, right, for how we might scan through different wavelengths. People have suggested, flapping this thing. I mean, there's all kinds of ways we might try to change the wavelength range, but we can only get a little bit at a time, is basically the problem.
It sounds like this is the point of the NIAC grant, is you're now going to spend the next multiple months doing the math and running through the different simulations and trying to figure out what's the right balance. So let's think about smaller versions and think about larger versions. So let's say that we had one target, like say we just wanted to know if there were Earth-sized worlds in the habitable zone at Alpha Centauri.
Okay.
Do you think, like, would a smaller version of the telescope get us that answer?
That's something you can do from the ground. So I think that's too close to make this one useful. So the thing is, the question is, what you want to do one star at a time?
Well, more like show the feasibility. That's all. Like, go after one target, one exciting target with a less complicated.
What's the technology development pathway?
Yeah, the bootstrap.
Is that what you're asking?
Yeah.
So I've been thinking a little bit about that. I think maybe one of the next steps might be to put something up as a CubeSat or a balloon project or something like that would put a smaller version up that could show the technology works by looking at, say, binary stars, or something that doesn't need the resolution of the larger, or that doesn't use the resolution and doesn't need to go as faint as the larger version. And so you can imagine doing something like that as a technology development pathway to get to this kind of a thing.
Like, I know that NASA recently canceled the Sophia telescope. Yes. But is that the kind of like is this wavelength of infrared that you're trying to observe, is this completely blocked by the atmosphere, and so you have to go up into the high atmosphere or out into space?
Right.
Okay.
Yes.
So a Sophia with this grating might be a nice platform to test out this technology, or balloons, or sounding rockets, or things like that.
Something like that. Yeah.
Yeah. Well, there you go. I think we just saved Sophia then. We'll talk to NASA and get this telescope installed ASAP, because who wouldn't want to know about other planets? But let's talk about so then I mean, you're talking about this one to do within 10 parsecs, but how big can this go?
Well, that's an engineering question that we don't know the answer to, because I mean, we're able to just draw a flat grating that goes out for a mile, and that fits perfectly well in our computer software. But then the engineers have told us these things are kind of hard to build. So you have to,
that's an engineering problem.
There is kind of one of my collaborators, actually the person who came up with the original idea for doing grating space telescopes, is Tom Ditto. And I got this idea from working on his concepts. But his idea was eventually these grating telescopes, you'd be able to like roll up a grating, shoot it up into space, and then unroll it on some kind of space platform that is built in place, right? And so in principle, you can make this as big as you want. And you don't have to fit the whole thing inside of a launch vehicle and have it, 100 meters or 1,000 meters or whatever it is, fit inside the vehicle itself. It just unrolls. And so, that's again another big technology development, which could come afterwards, to try to figure out how to do this. As it is now, when we're looking at 5 or 10 meter long gratings, that's still an engineering difficulty, because you need to have the lines in the grating stay exactly lined up over time, and you have to worry about temperature changes and how we're going to. I mean, we're talking about maybe dividing the grading up into smaller pieces that can be moved to calibrate them when things expand or contract, and so there's all kinds of engineering kind of in trying to figure out how to make the DICER version work with the 5 to 10 meter gratings, and how to get that supported and flat, and have the gratings all line up. And then if you make that work, then you can start to think about how we're going to roll something out and how we're going to have this thing built in space, and we're going to make something really big. But one of the things about space, though, is that support is a little easier in space than it is on the ground because we don't have gravity. So some things about making a big telescope in space might be easier in the future, but right now not.
Yeah. Now,
technology isn't there?
Does making the grating bigger? I'm trying to is it better to make the grating bigger or make the telescope bigger? So if you make the grating bigger, what does that get you? Like, instead of it being a 5 meter grating, what if it's a 50 meter grating with the same size telescope?
So if you have the same size telescope, but you get a bigger grating, then in order for the telescope to see the grating, you need to put it at a much more grazing angle. And so there's another engineering question of can you blaze the gratings so that you get a lot of diffraction at a particular angle that's very grazing. But then the other thing is that you will get a much even smaller range of wavelengths from the object. So having a bigger grating, keeping this telescope the same, will get you a higher diffraction limit, and it'll allow you to separate a planet from a star further away.
The planet farther from the star, or the star is farther from us?
So a bigger grating will allow you to see a planet that is angular, whereas angular distance from the planet is closer.
Right. So you're seeing Mercury.
So at the angular, so that's either a planet that's closer to a star or a planet that's the same distance but farther away.
Got it. Okay. So
either one would make the angle smaller.
Right. So I'm seeing a Mercury within the 10 parsecs, or I'm seeing an exo-Earth at 100 parsecs.
Right.
Right. Okay.
Exactly.
All right. And what if I make the telescope bigger, but leave the grating the same size?
Telescope bigger, then you get more light from the planet.
So I'm able to hopefully make better observations of the planet itself.
And you get more light from the planet, and you can make the angle that you're looking at it not as big, so you get more wavelengths.
Right. I see. I understand.
So there's a lot of
yeah. But I guess like this idea of the grating it is a simpler, like what you talked about, this idea of having to sort of really be concerned about the temperatures and so on. When you think about James Webb, I mean, it has these pistons underneath each of the mirrors, they're deformable, and they spent months just dealing with the cooling temperatures of the telescope and get everything nicely optic and, focus. So, I mean, I think we've seen space-based focusing system. Is a grating simpler than something as complicated as the beryllium mirrors on JWST with its pistons and so on?
Well, it's been put out there that it might be. I think we need to prove that.
Yeah.
We would like to kind of bootstrap a little bit off of the James Webb technology development that was able to do that kind of positioning and support and calibration of optical elements in space. I think some of that we might want to use in order to do this. But yeah, exactly how flat and how does the temperature change it and how will it be supported are not things we have solved yet.
Well, again, part of the NIAC grant. Materials.
That's what we're trying to figure out.
Yeah. So then I guess, what is the deliverable? What are you hoping to deliver as a report to NASA when you're complete?
what I would like to do is, this is a very short grant. It's over this year, so it's over by the end of December, probably maybe November, December timeframe. We have to be done. And so we're going to try to do is to have an optical model of the telescope, and that we'd like to use that optical model to try to do some of these optimizations, like can we get the size of the telescope down, and can we get the size of the gratings down? And it's, I think that people who do a lot of space projects have basically said that with the 3.5 meter mirrors, we're looking at something that would probably cost as much as the James Webb telescope. Just from looking at how big everything is, they think that's what it would be. And I would like to try to get it, the estimated, back of the envelope cost down to closer to $1 billion, which is a more manageable budget item. But to do that, we need to make the elements smaller, and we have to show that even if they're smaller, that the concept still works. The other thing that we'd like to do is to kind of push on what the science is that we can get out of it. Can we expand the science output that you can get from such a telescope to make it? It's pretty good science already. Find all the Earth-like
Answer
planets.
one of the most important scientific questions in human history. That's good.
But we need to kind of run an observing scenario, and say, okay, if we had this telescope, and we tried to observe these 60 stars, how long would it take, and what kind of data would we get, and are there any kind of gotchas that you would get from, say, our binary stars are going to be a problem, and is that going to screw us up? We don't know. And so we have to kind of run the simulated experiment and ask ourselves, what actually do you think we can do, and how long would it take to go through this whole science program? And are there other science programs that really could use this, that need to do high resolution in the infrared, for example?
That was my other question. What else could you use this telescope for when you're not, again, solving one of the most important scientific questions that humanity's ever asked?
Yeah. So, I don't know. If you think about things you might want to resolve at high resolution in the infrared, things that come to mind are, binary stars, or centers of galaxies that have active galactic nuclei, or star forming regions, or something. I don't know. Mm-hmm. But we need to kind of explore what could be possible in those regimes.
Right. But you could go back through the list of things that Sophia has observed and just kind of say, could we have helped?
Right.
Yeah, I understand that. Well, it's very interesting. Now, before you go out, sort of back to what we talked about at the beginning of the conversation about the Milky Way, you're working on a project where amateur astronomers can get involved. Can we talk about that?
The Milky Way at home.
At home, yeah.
So, Milky Way at Home has a long history, and it was originally created to solve a problem we're kind of having in science across the board, which is that once you have a lot of data, and there are a lot of sensors out there now in every area of science, you have a lot of sensors that are taking just a lot of data. And then you have models that you're trying to fit to the data. If you don't have very much data, you can probably fit all the data that's in there with 3 parameter models. Very simple model will fit it because you don't have much information. Then suddenly, when you have lots of information, and this was what I was running into with the Sloan Digital Sky Survey, I was trying to say, what shape is the Milky Way? And the Milky Way halo in those days would fit with 3 parameters. That's it. It just, the whole thing, 3 parameters. And now we know that it's completely filled with streams and clouds and lumps and different components and all this kind of stuff. And now you need, a lot of parameters. And it's very compute intensive. It takes a lot of computer power to do an optimization with 20 parameters even. It makes the problem really, really difficult. And so Milky Way at Home was originally designed to fit the spatial density, the space density of the halo of the Milky Way, just looking at the stars, how are they distributed in space, fitting 20 parameters at a time to strips of sky that were observed with the Sloan Digital Sky Survey. And so we did that, and I have a student who's still actually working on that now to do some data in the southern hemisphere that hadn't already been processed. But one of the things that occurred to us that, after having this resource of, a petaflop scale supercomputer that's donated to you from people all over literally every country in the world, and some countries that aren't even part of the United Nations. I mean, there's every atoll, there's somebody who has crunched a work unit from Milky Way at home. But just this enormous resource and our ability to use this enormous resource to fit parameters to data, we've kind of moved to trying to do a bigger problem, which is to take all these structures that we've identified in density, the tidal streams in the sky, and we'll run simulations of a dwarf galaxy falling into the Milky Way, being ripped apart, making a tidal stream, and then see if we can get that simulation to match the data that we have in the sky for that stream of stars. And so we, run hundreds of thousands of these simulations, try all different parameters, and then find the parameters that best fit. So I have a student who actually just graduated this past summer who was able to measure the shape and the mass density of a dwarf galaxy that fell in like 3 or 4 billion years ago and came into the Milky Way. And all that's left of it now is the stream of stars that got pulled out of it by the Milky Way's galaxy. And so we kind of are able to go back and say what initially fell in and how much dark matter was in it and how much stars were in it. And so we're working little by little to reconstruct where dark matter is in the Milky Way galaxy by running these, because the streams depend on it. It's getting more and more complicated as time goes on. The streams that we see in the sky depend on the dwarf galaxy that fell in. They depend on the Milky Way galaxy and what the dark matter distribution of the Milky Way galaxy is. In recent years, we've discovered that the Large Magellanic Cloud is maybe 10% of the mass of the Milky Way, and it's falling in, going past the Milky Way. And so its gravity also affects the shape and the disruption of these tidal streams. And the bar of the Milky Way has some effect on it, and other dwarf galaxies coming around might have some effect on it. And so you can imagine how complex these simulations could get as we add more and more and more complication to what the physics is that produces this tidal stream structure that we see in the sky. And so we're working hard to try to sort all of that out.
And so if people have some extra compute resources, do a search for Milky Way at home and
yes,
join the collective.
You can contribute your computer time to us.
Wonderful.
Yes.
Well, Dr. Newberg, thank you so much for taking the time to chat with me today. It's a really exciting idea for a telescope concept, very different than anything else that we've ever seen fly in space. And yet, if things work out, it could give us some answers to how common are Earth-like planets in the universe, which is,
yes,
I feel like one of the most important questions that we can ask, and I'm looking forward to the answer. So when you have that number, would you let me know?
Okay.
Wonderful.
Thank you very much.
Thank you. You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 60,000 people. I read every word, there are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verabioff, Josh Schultz, and Andrew Gross, who support us at the Master of the Universe level. All your support means the universe to us.